This is the video presentation of the paper Towards Personalized Head Tracking Pointing by Cicek and Manduchi from the University of California, Santa Cruz. Head tracking pointing allows users with limited upper limb mobility to move the pointer on the screen using their head, whose movement is measured by a user-facing camera. This video shows the first author, Cicek, using the Enable ViaCam head tracking system with a virtual keyboard. Our research aims to develop a new head pointing control that has higher accuracy and enables faster completion of pointing tasks than currently available. Our proposed method is to measure and characterize the user's natural head motion patterns and then build a control algorithm around those. In prior work, we collected a data set in which participants were asked to follow with their head a moving target on the screen. The participants' head movements, recorded by a camera, may indicate how they would naturally use their head to move the pointer along a desired trajectory. We are now asking whether it is possible to design a simple controller that can map the recorded image of a participant's head to the moving target's position at each time. We considered different visual features for this task, and for each feature, we regressed an affine mapping from the feature to the target's location. The first feature we considered is the nose tip. This video shows the moving target along with the location mapped from the nose tip. The inset video shows the location of the nose tip in the image. We also considered the 3D location of the nose tip. This video shows the location mapped from 6 facial landmarks as input. Here, the input is the pose, 3D rotation, and location of the user's head. We set 3 main tasks for our work. First, we wanted to determine which feature would enable the most accurate mapping. Second, we wanted to measure and characterize the discrepancy, defined as the difference between the mapped and the target trajectories on the screen. Third, we wanted to measure and characterize the angular discrepancy between the velocity of the mapped and of the target trajectories on the screen. Here are our main findings. We found that the feature made by 6 facial landmarks enabled the most accurate mapping among the chosen features. We observed that the mean discrepancy, bias, was space-dependent, with larger values near the edge of the screen. This suggests that a simple affine mapping may be insufficient to map a head feature to the target location on the screen. The standard deviation of the discrepancy was relatively large, 10% of the screen size, suggesting that the participants were not consistent in their head motion in response to the same target trajectory. Finally, we found that the standard deviation of the angular discrepancy was larger for diagonal head motion.